Okay. So, we are in the middle of the discussion of the compressor characteristics, and this is what we have been doing, and this we obtain these two non-dimensional group, and the total non-dimensional group here, 4 group of non-dimensional parameter, and then we have got this non-dimensional mass flow rate and rotational speed, and from there we have obtained these two flow Mach number and the rotational Mach number. So, now how we will get the characteristics curve? Now, all operating conditions for a pair of m dot root t by p and n by root t. So, this will provide similar velocity triangle, so that the vane angles and the airflow direction will match, and the compressor will yield the same performance in terms of pressure ratio, temperature ratio and isentropic efficiency. Okay. So, this is what the non-dimensional method of putting the characteristics implies. So, this will yield the same P naught 2 by P naught 1 and T naught 2 by T naught 1. Now, one can look at that two plots, number 1 P naught 2 by P naught 1 versus m dot T naught 1 by P naught 1 for varying n by root T naught 1, and second plot is the T naught 2 by T naught 1 versus m dot by T naught 1 P naught 1 for varying n by T naught 1. So, this would be, these two plots would be sufficient to provide the entire characteristics of the compressor. Now, also we can obtain the isentropic efficiency like eta c, which is defined as T naught 2 s minus T naught 1, T naught 2 minus T naught 1, and we can get T naught 2 s minus 1 by T naught 1 divided by T naught 2 by T naught 1 minus 1, which is P naught 2 by P naught 1 gamma minus gamma by 1, and this is T naught 2 by T naught 1 minus 1. So, typically if you see, instead of plotting this T naught 2 by T naught 1, this eta c is plotted. So, which is so before now considering the characteristics plot, consider the variation of P with respect to RPM. So, let us say the compressor is running at constant speed, let there be valve at the so this is what would happen. So, this is P naught 2 by P naught 1, let there be a valve at the delivery line of the compressor, and let us slowly open the valve. Okay. So, we have constant RPM, m dot constant, which is u is r omega. As m dot increases, v decreases, which means V r increases. So, there would be change in angle changes. Okay. Now, the first thing that could happen is that the valve is closed. So, when the valve is closed, so the m dot would be 0, and so this is a situation where let us say m dot 0. So, P naught 2 by P naught 1 would be A. So, corresponding to the centrifugal pressure rise because of the impeller on air trapped between the vents. However, at this condition no flows through the diffuser, hence no pressure rise in the diffuser. Now, as the valve is opened, the flow starts in the diffuser, hence diffuser starts adding some extra pressure rise, and then P naught 2 by P naught 1 starts increasing. And so, this is what happens. So, this is a point where let us say the curve is like this, and this goes like this and then come like this and come like this and somewhere like this. So, this is A, which we are just talking about. Then when the valve is open, the flow starts going through the diffuser, there is added this thing. So, this start increasing and reaches a point somewhere B. Okay. Now, when there is this is so called the efficiency, probably the maximum, and this point B, at B, P naught by 2 by P naught 1 is also maximum. So, it reaches the maximum value. Now, at very high m dot, flow angles are quite different from the design vent angles, and the air separation occurs at the vents and the pressure drops. So, this curve will start dropping from there, this maximum peak. Okay. And any further increase is m dot. So, this is where the m dot is increasing. So, further increasing beyond that point will result in the decreasing in the P naught 2 by P naught 1, and probably it reaches some point C. Now, hypothetically, let us say when the valve is fully open, the pressure ratio may drop to unity because of the very high losses. So, this will be here. So, all the power absorbed to overcome the internal frictional losses. So, this is a hypothetically this may happen. In actual practice, point A can be obtained, but the most curve between point A and B could not be obtained due to phenomena called. So, between A and B there is a possible occurrence of surge. Okay, this is another new term, and we are going to talk about this because these are all connected with the characteristics of the compressor. So, as I said, most of the situations between A to B, this curve may not be obtained because of the possible occurrence of surge or surging. So, surge means there is an immediate or sudden drop in P naught 2 with violent aerodynamic instability. Let us say the compressor is operating somewhere here, point let us say D, in between A and B, it is operating somewhere point D. So, the pressure curve at point D, so at D the pressure curve has positive slope. Okay. Now, if when it is here at point D, if the mass flow rate drops, so it goes in this direction. If the mass flow rate drops, so it will decrease in the pressure. So, P naught 2. So, from D, if m dot decreases, so P naught 2 also drops out. So, this mass flow rate decrease is accompanied by the fall in the pressure rise. Now, what may happen if the pressure of the air downstream of the compressor does not fall quickly enough. So, there would be a positive pressure gradient exist exists between compressor outlet and the downstream air compressor. So, when this happens, so there is a possibility that positive pressure gradient may occur. So, air reversal takes place, okay, and starts to flow towards the compressor outlet. So, the pressure ratio drops rapidly. Now, when the pressure at the downstream of the compressor falls substantially, the compressor can pick up again to repeat the same cycle. So, this occurs at very high frequently and is very much detrimental to the engine, and this is called the sort of surging phenomena, and when that happens, the surging does not occur immediately at operating point, moves left to B, because initially the downstream pressure may fall at a faster rate than P2, but as m dot is reduced, sooner or later the compressor will go into surge, unstable between A and B. So, this is what is important. So, that means between point A and B, most of the operating procedures are not, or the compressors rather do not operate between these 2 points, because surge may occur. Now, beyond B, what is happening there? Beyond B or between B to C, if you look at the pressure curve has negative slope. Okay. So, this operation between B to C is also stable. In this range, if m dot is decreased, let us say somewhere here, if m dot is decreased, then that can be accompanied by rising the pressure loss or the P2. So, typically surging depends on the mass handling capacity of the turbine. Probably it starts to occur in the diffuser vanes, and which has already have an advanced pressure gradient due to diverging passes plus frictional forces. So, now the tendency to surge increases with the increase in number of diffuser vane. So, when there are several diffuser vanes for one impeller channel, it is very difficult to split the air equally to all the vanes. So, that is another problem, that if you have multiple these things. So, the channel with low mass flow rate will go into surging first and the other case. So, air will then start to flow up the channel. So, does the other end and then cause surging. That is why the number of diffuser vanes are less than number of impeller vanes. So, you can see this is another important criteria while designing these compressors, because if that happens, there is a possibility of occurrence of surge. Now, since each is supplied by several impressors, so this can be evened out. Now, even in this case, at low mass flow rate, all the diffusal passes will go into surge simultaneously, adding a limitations between B to C. So, there is still a possibility. So, one has to be careful. Now, there could be another point where let us say E, where at E, if the m dot goes up here. So, let us say at E, m dot goes up. So, as pressure goes down, which means density goes down, which means VR goes up. So, alpha increases. Okay. So, after certain point, it is possible to increase m dot any further. So, this is called the choking. So, this is called the choking in a compressor, and that means this corresponds to the maximum flow rate of the particular RPM for which the curve is drawn. That means that m dot max condition is obtained. Okay. So, this is what is going to happen. So, now apart from the surge, so we can look at the compressor stall. Okay. Now, stall is common to both axial flow compressor and centrifugal compressor. Now, centrifugal compressor both of them can go in surge and stall. Now, stall is typically when the flow separation takes place. Okay. So, this happens in guide vane and blade passages, on blade passages and of design conditions. So, when the incoming flow angle is greater than the stalling angle, the flow separates and leads to the stall. So, what happens with the stall? There would be a sharp reduction in delivery pressure and unsatisfactory engine performance. So, at design conditions the flow enters the passage smoothly. Okay. So, if you see, this is my aerofoil and this could be the velocity triangle for that. So, this is u, this is W1, this is alpha, this is V1 equals to VR1. So, this is the rotation omega. So, what it gives, that tan alpha of blade is tan alpha of flow. So, which means V1 by u, which is design, equals to V1 by u, which is flow. So, that no flow separations, that means no stall. Okay. So, same thing is true for the diffuser vane on the compressor. If tan alpha of the flow greater than tan alpha, which means tan beta is less than tan beta of design. So, there is, which means the VR by u greater than VR by u design, which is known as negative incidence flow separation. Okay. Or if VR by u less than VR by u design, this is called positive incidence of flow separation. Okay. So, which means stall depends on mass flow rate RPM. So, as m dot A or speed increases for constant RPM, VR goes up, which means VR by u becomes VR by u design. So, which causes negative incidence. Okay. Now, when u is increased for constant VR or constant m dot A, so VR by u would be less than VR by u design. So, that is a positive incidence separation. Okay. Now, this depends on all these things, there could be another situations where it called rotating stall, which means, so since these are the rotating conditions, so let us say we can have passage like A, so let us say B, the airfoil C. So, this is a passage, and then this could be A, this could be B. Let us say there is the separation, passage C, like this. So, this is how the flow comes in and it distributes in these passages like this, it goes like this. So, when one passage actually stalls, the flow gets deflected. So, essentially the flow is supposed to come in this direction, but see, due to the stall the flow gets deflected towards another passage. So, when that happens, so alpha for one of the neighboring passage also increases. Let us say if for A alpha increases, then passage C alpha actually decreases. So, this will lead to the stalling of that passage A, and then that passage has already stalled originally recovers, since alpha in the passage B decreases. So, now the stall keeps on from A, it will move to B, from B it will move to C. So, the stalls actually from one blade passage to another blade passage to another blade passage, because of the rotation it goes on shifting, and multiple passages can go on stalling situation simultaneously. So, this is what called the rotating stall, and typically this is a precursor of surge. If multiple passages go on stalling, then that can lead to the surge, and this would be a detrimental effect. Now, at the impeller I, the stall rotates in opposite directions of the rotation of impeller. So, this causes aerodynamically induced vibration, so that resulting in fatigue failures in other passages also of the gas turbine. Okay. Now, coming back to that characteristics curve. So, when you come back to that, so we are considering operation at certain point. So, let us say this is how this should go. This is C, somewhere E, B, point A, D, and this is PRC. So, point D, which could be a point of surge. So, we got this curve. So, between B to C, m dot increases, so P decreases, which means rho decreases, which means VR increases. For a constant omega, this means the increase in resultant V. So, that goes up. So, the angle of incidence at diffuser leading edge. So, the operation is typically limited between D to E. So, D one can call surge limit, and E one can called choking limit, which is the m dot max condition. Okay. So, now this particular curve PRC by m dot is for a fixed RPM. Now, once we change the RPM, we can get similar curve and get the complete characteristics plot. So, let us say 0.2, 4, 6, 1.0. So, this could be 2, I mean 3, 4, 5 like that. We have P2 by P1 and this side we have m dot T naught 1 by P naught 1 divided by m dot T naught 1 by P naught 1 design. So, what we get? We get typically this is one limit. So, this is another limit and we get curve like this. So, and this is called maximum efficiency line. This is surge line and this could be 0.6, 0.7, 0.8, 0.9, these are the choking line and the variation is n by root T1 divided by n by root T1 design. So, this is how the speed varies. So, for different RPM, so we get this pressure line. Okay. And what it does, that as n goes up, rotational speed goes up, which means W T omega goes up. So, more work involved and hence higher pressure rise. Okay. And as we have discussed earlier, the n is limited by the structural stress. So, which essentially controls the U for a particular speed. So, similarly, one can find the curve for eta c versus m dot t by T naught 1 by P naught 1 with the m dot T naught 1 by P naught 1 design. So, you get typical curves like this. So, these are again maximum points which are varying n by root T naught 1 divided by n by root T naught 1 design. So, eta c percentage varies in the same manner as PRC, same variation as PRC. Beyond an optimum PRC, so beyond optimum PRC, eta c actually decreases. Okay. And if you look at the, so these are the eta c max condition like this. So, eta c max pretty much remains almost constant with varying speed. So, the compressor should be designed, it approaches along the, so the design as it design that it approaches along eta c max. So, this is sort of an gas turbine design criteria. So, these are the two curve one gets. So, you can have 20, 40, 60 some number 80. So, these are some particular number that has nothing to do with that. So, one is this pressure versus non-dimensional mass flow rate and it gives you the surge line and choking line, and other case you have the isentropic efficiency versus non-dimensional mass flow rate and for varying speed, and you get these two important characteristics curve. And from this curve actually one can determine the characteristics of an compressor. So, this is not only true for centrifugal compressor, this would be also true for the axial compressor, as we do the discussion in the following lectures, that they also have the similar characteristics curves, and the variations of the efficiency and pressure rise with respect to speed and non-dimensional mass flow typically the same. So, we will stop here and continue the discussion in the follow up lecture.